All right, so Unit 4 starts our look at applications of derivatives. Now we're going to start with related rates. So related rates are probably like your all-time favorite algebra problems, like this one. All right, in reality, related rates should be approached with a set strategy. If you need to pause and write these down, feel free to do so. I'm going to go through them rather quickly. So step one, as should be the strategy for any math problem, read the problem carefully. Make sure you know what you're being asked. Draw a diagram if possible. Sometimes just getting a picture will help to determine the way that you're going to solve that problem. Introduce notation, variables, and other things. Assign symbols to all quantities that are functions of time, and that's the key for a related rates problem. Our functions are all with respect to time. Express the given information and required rate, if that's what you're solving for, in terms of a derivative. Write an equation that relates the various quantities of the problem. If necessary, use the geometry of the situation to eliminate one of the variables by substitution. Use the chain rule to differentiate both sides of the equation with respect to t. I'm going to use the chain rule and implicit differentiation. Because t will not be one of the variables. Substitute the given information into the resulting equation and then solve for your unknown rate or unknown quantity. All right, so here we go. A storm at sea has damaged an oil rig. Oil spills from the rig at a constant rate of 60 cubic feet per minute, forming a slick that is roughly circular. Assume the slick is 3 inches thick. How fast is the radius of the slick increasing when the radius is 70 feet? Now, one thing that we are going to assume is that the thickness of that oil slick does not change. It's going to remain at that thickness throughout the entire time. So the slick is going to expand out, but not down. All right, so draw a picture of the situation. Oil rig. In the water. Oil slick. volume of the slick is changing at a rate of 60 cubic feet per minute. I know the thickness is 3 inches, and I know the radius we're looking for is 70 feet. We want to find the change in radius with respect to time. So we need a formula that will combine radius, height, and volume of the shape of the slick, which is a cylinder. So the volume of a cylinder is pi r squared. So we're going to take the derivative with respect to time, dv over dt. Pi is just a constant. R squared, derivative of h, is dh over dt. Again, pi is a constant. In this case, we're going to take the derivative of r squared. So we have the h, and derivative of r squared is 2r times the derivative of r, which is dr over dt. So there's where the chain rule comes into play. Plug in what we know. We know dv over dt is 60. We know r is 70. dh over dt, the height, is constant, so it's changing at 0. The height is 3 inches, however, everything else is in feet, so we're going to convert 3 inches to 1/4 of a foot. That 0 helps out. It eliminates everything on that side of the plus sign. If I multiply out the 1/4, the 2, and the 70, I get 35 times pi. If this were the AP exam, I would not need to simplify or reduce. Felt the need to do that. Actually, I want to rewrite this a little bit because the pi is actually in the denominator. And if you wanted a decimal approximation, this would round to 0.546. Or if you just truncated it, which you can certainly do on the AP exam, 0.545, in both cases feet per minute. All of those would be acceptable solutions. Example number 2. Two roads intersect in Newtonville. One car is approaching the intersection traveling east at 60 miles per hour. Another is driving away from the intersection traveling north at 50 miles per hour. How fast is the distance between them changing when the first car is 5 miles from the intersection and the second car is 10 miles from the intersection? Again, drawing picture. This car here, I'm going to call it A. And it's traveling east at 60 miles per hour. This other car I'm going to call B, traveling at 50 miles. So I want to know when this is 5 and this is 10, how fast are they traveling from each other? I'm trying to find an equation. It helps if I make one little addition to my drawing. We have a right triangle. And so the equation that we're going to use, a squared plus b squared equals c squared. Take the derivative. Derivative of a squared, 2a dA over dt plus 2b dB over dt equals 2c. If you wanted at this point, you could divide everything by 2 to get rid of those constants. That would work. Otherwise, you can leave them in there, and in solving the problem, the 2's will take care of themselves. The way the picture is drawn, A is 5. dA over dt is not 60 because the car is traveling east. That leg of that triangle is getting smaller, so the rate of change is negative. The other leg has a length of 10, and that car is moving away from the intersection, so that leg is getting larger. So that is a positive 50. I don't know what C is, but I can calculate it because 5 squared plus 10 squared is going to equal C squared. C squared is 125. Is the square root of 125. I would leave it in that form. Don't round. If you round, round only at the end. And I'm trying to find dC over dt. Solving then for dC over dt. Again, on the AP exam, you would not need to reduce that. If you felt the need to reduce that, you would get 17.889 miles per hour or 17.888 miles per hour. In either of those solutions are acceptable on the AP exam. Information, common formulas that you'll see on related rates problems, volume and surface area, which if you have your textbook, those are on that inside front cover. The Pythagorean theorem, law of sines, law of cosines, also on the inside front cover of your math book. If on the AP exam you are asked to use one of these formulas, normally they would give you the formula, especially volume and surface area problems. Assignment on page 260 and 261, 1 through 6, 11, 12, 19, and 29 will give you a good feel for what related rates problems look like